the plan for today is roughly in the first hour, I'll continue what the discussion of the finite range approach to the renormalization group that we began last time, and hopefully there'll be some time, roughly the second hour, or maybe a little bit less, where I show an application. Let me first begin with a recap from last time. So we started with a Gaussian reference measure, which we think of as a free field. Sometimes we add a mass term for convenience, but we're interested in the case when the mass term is essentially zero. And we decomposed this Gaussian field, or equivalently its covariance, into a sum of covariances denoted C sub j, which go from 0 to n, and which have the finite range property that the covariance vanishes if the distance between the 2 points is bigger than a half L to the j. And so n is the size, or is related to the size of the space we're looking at here, which is a torus of side length L to the n. And you should think of L as fixed, maybe 2, and practice will soon see it. It's convenient to have it a little bit bigger than 2, but fixed, and n going to infinity. And then there is a corresponding decomposition of space into blocks consistent with the sizes of these covariances. And the finite range property gave this very nice and convenient factorization property for the Gaussian field, which means that functionals supported in two sets, x and y, and these sets x and y are unions of blocks of the corresponding scales, which we call polymers. So polymers are just unions of blocks, and x and y here. That for polymers that do not touch, these factorization, or these expectations factorize. And that's a very convenient property, which this approach to the renormalization group is based on exploiting. So often, well, essentially all other approaches in the literature, one can work with weaker factorization properties, say exponential decay of correlations and so on, and these require additional ingredients then, such as cluster expansions, which are involved. And the beauty of this finite range approach is that these are not needed. So then next, we're interested in studying the renormalized potential, or to be more honest, we'll be looking at the exponential of the renormalized potential, which is this Zj. So it's, in other words, the integrated partition function with an external field phi, if you like. And so the renormalized potential would be the logarithm. Sorry, was there a question? No. And so the parametrization of this Zj is as follows. There's a sum over these polymers X, so subsets of blocks. You can see in this picture a red part and a yellow part. The red part, which we think of as a good part, is where this Zj is represented by an approximate version of the renormalized potential. That's this Vj. And the yellow part is a region you may think of as bad, where there's an error term, which is denoted by this Kj. So the Vj and the Kj, they have different factorization properties. The Vj, will often work, or will usually work with the exponential. So I'll write I of x for the exponential of minus v of x. And so v of x is local. It's a sum over points in x, roughly speaking. That's the way to think of it. So it enjoys this block factorization property. If you evaluate I at a set x, it's the product of the i's corresponding to the blocks in x. K, on the other hand, only has a weaker factorization property, which is that it factorizes over components. And we saw last time, well, that it's easy to write down a choice of the renormalization group map. So we start with coordinates vj, kj, and want to map them to vj plus 1, kj plus 1, say. So here, just denoted by tildes, that go from that are defined on blocks of scale j plus 1 rather than j, and that preserve the partition function in the sense that if we take the expectation of the partition function zj, we'll obtain a representation of the partition at the next scale this way. So this simple example of the reblocking map had some deficiencies. One was that we were in fact allowed to pick the new potential, which is given by this I tilde. Remember, I tilde is e to the minus v tilde, if you like. It was allowed to be arbitrary, and so clearly this is cannot be a good choice. And what we're going to see next is how to make a good choice. And so, well, to understand how to make a good choice, we need norms to measure how big the error is. And I gave some examples, and the key properties that we want is the submultiplicativity property, which is this one, and then the contractivity of the expectation. And we saw two examples that have these properties. These examples I explained are not good enough for applications, but they illustrate how this method works. And then we studied a prototype for the simple reblocking map, which is given by this F bar. So you start with a polymer activity F. So it's just a function of a set X, and F of X is itself a function of the field inside X. So this one. And we did the simple reblocking map, which is to define a new polymer activity on scale j plus 1, denoted by F bar, by just summing over all polymers inside the j plus 1 polymer, summing over all polymers at scale j. And so this example is where we stopped last time. We were trying to measure the size of F bar. So we want to take the norm of F bar. So maybe I should also recall that we discussed norms for F of X, for single F of X, and we can make it into a norm on these full polymer activities F, which are collections of F of X, one X for every set. So one F of X for every set, by taking a maximum over all sets. And we can also put in this exponential weight, which is a good thing to do because it measures locality. The exponential weight will enforce that F of X becomes smaller and smaller the larger X is, and that'll capture the property we want, that the representation is approximately local. So this is the example where we stopped. We were looking at this simple reblocking map. We're trying to measure its size. We have to take a maximum over all sets U, but we just looked at a single one right now. Was there a question?
Okay.
No. No question?
I think
okay.
Maybe somebody should close his microphone.
Two times. One is tomorrow morning, 9 o'clock, and the second one.
I think you can mute everyone.
Okay.
Can I?
I think.
I don't know who can turn the micro off.
Let me see.
Roland, I think you probably can.
I'm just trying. I'm not sure how.
Phone you back.
I don't think so.
Thank you very much.
Well,
you're welcome. It's okay. Bye-bye.
Maybe just kicking him right away, and then he will come back with a turn off microphone, maybe.
Yeah. Well, seems to be okay now.
Let's hope he doesn't have another call. Okay.
Okay. Good. So then we can. So we were looking at So we want to estimate the norm of this F bar. So that involves a maximum over these polymers at scale j plus 1 of F bar of U, and use this polymer at scale j plus 1. And we just looked at a single block. So that's the block shown here. And we're trying to estimate what the norm contributed by the single block is. And what we saw is that when you do that, you see a factor L to the G, L to the D coming up, multiplying the norm of the previous scale activity F. And this factor L to the G is just the combinatorial factor from placing a J block in the number of ways of placing a J block inside a J plus 1 block. There's L to the D ways to do that. So that's shown by this picture here. So this looks bad because we ultimately are interested in a contractive estimate rather than one that expands. And so the goal is going to be to show how to get a contractive estimate. Okay, so here I'll continue. So first, let me so this factor, so basically the problem we encountered is that, say, if we look at a block, say, at a single block, which I'm going to put in red here, of scale j, inside a block of scale j plus 1. Say we look at a single block, that's the red one, and we're looking at the closure x bar, which is the smallest j plus 1 block containing this block x. So x is the red block, and then we're looking at, say, x bar, which is the full block here. Well, these are obviously the same. There's one x, one j block x, and if we take its closure, it's still a single block. On the other hand, if we consider the scenario where x is not a single block, but let's say it consists of many blocks. Say x consists of let's say all of the blocks in here. So then this is L to the D, but the number of blocks in X bar are still only 1. So there's a huge gap between the size of X and the size of its closure at the respective scale. And it turns out there's a general principle here. There's a combinatorial principle encoded by this lemma, whose proof you can find, for example, in David Bridges' Park City lecture notes, which are linked on the website. We'll make an assumption, say that L is bigger than 2 to the D plus 1. So in 3 dimensions, say this is 10. It's a convenient assumption. Then there's a geometric constant. Geometric meaning this constant eta only depends on the dimension. And it's strictly positive, such that if X is a block at scale J, and the number of J blocks in X is at least 2 to the D plus 1. So again, this is just a finite number. Then the number of blocks in its closure at scale J plus 1 is much smaller than the number of blocks at scale J in X. So much smaller being shown here by this positive factor 1 plus eta between the ratios. So this is a combinatorial fact. And it turns out that it implies that all sets or all polymers X, which have at least 2 to the d plus 1 blocks in them, they're unproblematic. They're easy to handle. And I'm going to show this next. And it motivates this definition. Sj is the set of connected polymers, scale j, such that the number of blocks in X is at most to the d. These are called small sets. So small sets are going to be the dangerous one. And every polymer that's not a small set is called a large one. And the large ones may seem like the concerning one, but it turns out those are the easy ones. David Bridges likes to say that the large sets scare everyone except for him. But the next example is going to show that really they're easy. It's really the small ones that are dangerous. So suppose we're looking at a polymer activity that is only supported on large sets. So f of x is 0 if x is a small set. And let's try to estimate the norm of f bar. So f bar u at scale j plus 1. It's well bounded, as in the previous example, by the sum over all connected polymers at scale j, whose closure is u. And then we take f of x, j norm. Now, by definition of the norm of f without the argument x, which was given by a soup with an exponential weight, this is less than the norm of f. And then we have the sum x pj c x bar is u. And then there's a factor a to the minus the number of blocks in x. So that was exactly the definition of this of this norm. So now we can use this this fact star to bound bj of x in terms of bj plus 1. So what we get is this is less than this norm of f always carries through a to the minus 1 plus eta, number of blocks j plus 1 in u, and then the sum only there's only one. It's just only once in the sum at this point. So we can bound the sum very crudely as follows. So what does this sum mean? Well, we have some polymer u, say u may look like this. And then we're looking at all x inside u, which are just say subsets like this inside u, and we can bound this sum by simply the number of all subsets of this set u, connected or not. And the crude bound is just, well, the number of subsets of the set is 2 to the number of elements. So it's just 2 to the L to the 2 times the number of j blocks in u, which is the same as 2 times L to the d times the number of j plus 1 blocks in u. Make a little bit more space here. So this is an incredibly crude bound, but it's sufficient. So everything on the right-hand side involves j plus 1 blocks in u now. So we can write this bound. So it's this norm carries through, a to the minus bj plus 1 u. I'm taking this factor out because remember, we want to bound the norm of f bar, so we want to take this factor to the left-hand side. Actually, that's how the norm of f j plus 1 is defined. But then we have this eta left. So what factor do we have left? We have a to the minus eta, and then there's a 2 to the L to the D, and this is to the number of j plus 1 blocks in U. Now, the parameter A is, we can choose it however we want. A is a weight that we can choose. And we can choose it to be such that a to the minus eta is bigger than L to the 2 to the j. So this is for appropriate for a chosen correct. This is less than a to the minus, say, 1/2 eta. And a is large. So this is a tiny, this is a factor smaller than 1 if we want to. So the upshot is that, well, this is much less than norm of fj times a to the minus beta j of u, because it's multiplying this additional term, which is much less than 1. So this is really all that's needed for these large sets. The norm of at scale aj plus 1 is much smaller than the norm fj. So upshot, large sets.
Excuse me, can you say it again? Why you have the last inequality? Because
The last
you had...
sorry, bj plus 1. Sorry.
Okay.
Yeah. Now it's okay. Thank you. So yeah, I'm just bringing for the final arrow, I'm just bringing this bj plus 1 to the other side, right? So anyway, the upshot is large sets, which initially seem concerning, they're actually easy. So they contract for geometric reasons. The norm does not play a role. All that matters is that it has the right factorization properties. Any norm that has the right factorization properties, large sets contract. So really, we're down to small sets. Those are the only ones we need to worry about. And so that's the next point. And the next and basically final point that I'll explain how that works. And this Slava is where the extraction of the local parts will come in. So so this is called extraction of local parts. So we're down to explaining what happens with small sets, and what we'll make an assumption, and this assumption is I'll explain, but I think it's what Slava has been waiting for. We'll assume, so we're only looking at X, which is a small set now, so meaning it's a union of blocks at scale J and at most 2 to the D of them. And we assume we can write this K of X as a sum of 2 terms. One I'm going to call log X of K of X, and well, the other one is 1 minus this. So we want to write it as a sum of 2 parts. And the basic property we want is that if you take the norm of 1 minus log X kx, this is much smaller than L to the minus D, the norm of K. This is so let me comment a little bit on what this log X of K of X is supposed to be. Anyway, so I'm going to explain this a little bit, but then this is the kind of assumption we want to make, that we have this structure and then see what we can do. So in practice,
excuse me, is there an assumption on the other part? Because else it's always true. It's
well, yes, we want a good point. So we want the other part, say it's bounded, say. It's a good point. So say we also want something that log x, k of x is, say, bounded.
okay.
So in practice, this log x is going to be something like this. It's essentially explicit. And in the phi-4 type models, it's this it's of the form of a phi-4 polynomial. So it's explicit of the form needed to be considered as part of VJ. So I think, let me write, so think about it as log x, k of x, is given by a sum over the points x and the set x, say, and then there's 1/2 some constant gk of phi x to the 4, 1/2 new k phi x to the squared. Usually one also has to add, say, a term like this. This is the kind of this is what it usually is in practice, and where these gk, these are just 3 numbers. It's determined by these 3 numbers in this case. And how are they determined? For example, they are determined by matching the Taylor expansions for constant. So phi is a field. You can take a constant field, and then you can compare the Taylor expansion, say, of the right-hand side and of k of x, and match these constants so that they agree. And this zk is determined similarly, but that's I'm not going to explain this here. In fact, there's a very nice general story of how to do this based on, or motivated by, or based on polynomial approximations of functions that David developed with Gordon Slade in a paper that I also referenced on the website. So let me put a picture here for a very general way how to get such an approximation. Anyway, a key feature is that we'll be using is the following locality property. So this log x, well, it's a sum over x. So you can write it as first the sum over blocks in x, and of something that I'll denote by log xb of k of x, where this log xb is simply the same, where I restrict the sum to b. It's the same as before. It has this locality property that we can decompose the sum over x into parts that are associated with blocks. And so maybe at this point it would be, so of course you can write down this approximation in the way I explained by matching Taylor expansions. This is the point where when you try to prove this estimate, say, you realize that you'll run into problems when you use the L infinity norm. This 1 minus log is a kind of Taylor remainder, and you cannot control a Taylor remainder in L infinity norm unless, say, you have an analytic. Anyway, so this is the point where you realize that the L infinity norm I presented is not going to work. You'll also realize that the norm I showed for fermions is much better. Sorry, was there a question?
I was saying that the second equation also looks very problematic in L infinity norm because
yes, it's the same issue exactly. The second expression is equally bad. Yeah, so they go together. So this is where you see that the L infinity norm is not going to work. But you'll also see that if you look at this example of fermions I presented, that except that there it pretty much does work. There pretty much does work. There's some subtleties which I didn't explain corresponding, for example, to this gradient term, but if you ignore that, it essentially does work. But that's where the problems for bosonic or probabilistic variables appears. The L infinity norm doesn't work, and you'll need to do something else here. You'll need to weaken this requirement a little bit, first of all, and secondly, the choice of norm is that gives a reasonable version of these properties is more delicate. But let me, for the time being, assume we have these properties. So the game is to get approximate version of these so that the rest works.
Excuse me, just to, an intuition of what you mean by locality is the same as kind of extensivity of the.
Yeah, exactly. Yeah, exactly. That's what I mean. That's probably better way to. Yeah, this is a sum of, so this log x k of x is a sum of the terms. It's extensive. Yeah.
So you like something like a L1 norm or something like this?
Yeah. Well, I'd like to. Okay. This gets me to the next point. The point is, we want to basically. For X's general small sets, so there are not too many of them, but more than there are blocks, right? Blocks is a small set, but 2 blocks is also a small set, etc. We want to cancel somehow. We want to cancel all of these small sets in the sense that we want to effectively replace. For X a small set, K of X by 1 minus log of it, so that we get a good contractive estimate. So if we go back to the example here, so here we assumed there are no small sets, then we got a contractive estimate. That was good. Now if we make a similar approximation where we assume that K of X is always replaced by 1 minus log K of X, well, then we get a contractive estimate just by assumption. Again. So what we want to show is that we can effectively replace K of X by 1 minus log K of X for X small. So roughly speaking, want to change coordinates. So we have coordinates V and K. And we want to change them. We want to now use the freedom that we can change V to something else, and that'll also change K to something else, to move log x K of X from K to V, so that effectively K prime is roughly speaking given by 1 minus log of K. So we want to remove it from K and put this part into the V coordinate. The difficulty is V is only indexed by blocks. It has the block factorization property. So blocks. On the other hand, we want to move k of x for x, which is a small set, which strictly speaking contains the set of blocks. So you can imagine that if you want to remove k on a block into V, this is possible because both are indexed by the same blocks. But it turns out we want to move much more into the V coordinate than is given by blocks. And this is made possible by the locality assumption. And so let me, to explain this, let me first assume we only want to cancel blocks. Rather than small sets. Then the simple reblocking map from last time suffices. So what is the simple reblocking map? Let me just scroll up a little bit. That's the advantage of having a tablet of the board rather than a board. That's this one, right? So this is the one we saw last time at the beginning. We had the simple reblocking map. It was a little bit concerning because this I tilde was arbitrary. We could put anything. Well, what I'm going to tell you now is that if you choose this I tilde correctly, well, then you can basically remove anything on a single block from K. So let me. So this is the example simple reblocking map continued. So rather than using any I tilde or V tilde, we'll use a specific one. And so what does this example say? So the claim is that there is a map. So there's a choice of map that goes Vj, Kj to say Vj plus 1, Kj plus 1 as follows. So here, now I'm not using any choice for the next scale. So Vj plus 1 is what was previously V tilde, or I tilde was e to the minus V tilde. So here I'm using the following explicit choice. I'm using one term is, this is first order perturbation theory. So I'm taking the next V to just be the exactly what we saw as first order perturbation theory before, except I'm only doing it on a single block. So this is also at a single block. And then I'm adding, then I can subtract something else, and the only assumption I'm gonna be making is that this, well, it has to be also indexed by blocks, and it'll have the same form. And the assumption I'll make is that this thing is of order K. So we're assuming that we have the norms on K, and that we can take the norm of this quantity as well, and it's of the same order of K. And then with this choice, this map Kj plus 1, K tilde before, we can write down what it is. We had a formula last time. I'm not going to write down this formula again. I'm just going to extract the part we're interested in. I'm claiming that there's a linear part, or a part that I call L for linear, that's linear on K, and other terms which are of second order, and second order here means unproblematic. And what is this L? where Lj plus 1 of u is given by the following expression. It's the sum over connected polymers of scale j. So u is at scale j plus 1. So it's a sum. So it's like the reblocking map. There's a term like this that'll appear. We saw that before already. That this was I tilde to the u, take out x, and then there's the expectation in here, and we have the k of x. That was what we had last time, and then we also have another term which was called delta I to the x. And well, this delta I. With this, so this delta I with this choice is, well, it's determined by this choice of Vj plus 1, right? So delta I was given, it's e to the minus Vj b of phi plus zeta minus e to the minus Vj plus 1 phi. And this is if x is a single block, say. And then it's to the x to it's going to be product over blocks in x. So and we'll take the expectation of this. Now, if you use this choice of Vj plus 1, what you'll see is that this would, after taking the expectation, will become the expectation of essentially Q. So if x is a single block, and then there are order v plus k squared terms. Now this Q, I've not made any assumption on this. Previously, I tilde was arbitrary. Now this Q is arbitrary, but I can make a choice of Q now. I can choose this Q exactly so that it cancels log of K. So choose Q of B to be log B of K of B. What happens then? Well, I guess there's a minus here also, I think. Anyway, you can put a minus or not. I think there's a minus here. So if you choose K of B to be log B of K of B, what does it do? Well, it replaces K of B by 1 minus log. So this is what we wanted. So we get a good estimate for this dangerous term indexed by blocks. Now,
sorry, Roland, hi.
Yes.
One question. So before the second, I mean, natural correction was to the covariance was to explain the second order. Do you have more than that in the queue?
I'm just doing first. I'm showing what I'm showing. It's a good question. What I'm showing here is how to make first order perturbation theory correct. So even to first order, there is I'm showing. So we want to keep track of the of the effective potential to first order, say. So somehow we're not trying to keep track explicitly, say, of the effective potential to second order. That's all going to be done through estimates. And that's sufficient in a case where the second order doesn't play a big role. So for example, these are, say, a 5-4 model. This would not be sufficient in 4 dimensions, but in 5 dimensions.
Okay, okay, thank you. Okay.
So in 4 dimensions, you're right. This wouldn't be sufficient even for a single block, but in 5 dimension would.
Okay, thank you.
So anyway, this principle explained how we can cancel a single block, but it doesn't. But remember, we want to cancel all small sets, not just the blocks. And Well, that's where the locality comes in. So this is the end of the example. So what do we do? What about the remaining ones? So in other words, X is a small set that is not a block. So it has at least 2 blocks, in other words. We have made the assumption, this locality assumption, that, well, K of X can be written as the local part, which I'm going to denote by J of X now. So this is log X, K of X. And then there's the remainder, K of X minus J of X. And the locality property says that J of X is in fact the sum over B of terms JBX, which are the log BX, K of X. So we're not considering, so we're only looking at X, which are small sets, but not a block. So we somehow assume that blocks will be okay anyway, as the previous example showed. By making a suitable adjustment of the V coordinate, you can fix what happens on blocks. So we're just considering what happens for X not a block. And so what you can do is these JB of X, X is not a block, so I can just define whatever I want this to be when X is a block, and I'm just going to set it to be minus, well, doesn't matter how I define it. I'm just put whatever I need to put to get the following property. So this so this just corresponds to JB. Maybe it's clearer if I just write down what it is. So it's minus the sum over X, which are small sets. Oops. But not blocks. And X contains the block B. And then we take these JBX from before. So this, okay, why are we doing this? Well, we're doing this, so I'm going to copy the example from before, because we're going to make some, so this example from before, copy and paste it here. We want to make an adjustment. So, so I want to improve the statement further. So the statement is there's a choice. It's again, there's a choice of this map. Oops, that's not what I wanted to do. Maybe it would have been quicker to rewrite this, but anyway. The VJ choice is the same as before. And the KJ choice, well, is not the same as before. I mean, I still divide it in the same way. There's still a part which I call L, but it turns out you can put, so this, let me just move this a little bit so I have some more space. The point is we can put an additional term here. It's minus the sum of B in the so basically we can add this additional term for free under the assumption that this condition holds. So this is the point, and so the conditions are again provided this QB is of order k, as I assumed above, and these JBKs, not JBX, are also of order k. And they satisfy this condition x, j, b, x is equal to 0. So what happened? Well, basically, one can make this orange term. I remember you can't see orange well, right? So I'm going to use a different color. Green. One can make this green term here appear in this formula where it wasn't before. Of course, it has to reappear somewhere else. And it turns out it's a resummation. And when it appears somewhere else, it appears exactly like this, as 0. I was going to go through this computation in detail, but I'm afraid maybe I'm going to, it would take some time. I'm not sure. It's probably better to explain the example rather than going through it in detail. But the principle is again, it's a similar combinatorial arrangement. You make this term appear here, you make it appear somewhere else, but it's resummed so that it appears as this 0. So what's the upshot of this? Well, the upshot is that for x, which is a small set but not a block, we now have kj of x minus sum over b, j bx, which is exactly 1 minus log x k of x for all small sets which are not a block. So this is what we want, right? So this is good. And what happens for blocks? Well, for blocks, we now have instead, well, there's also the expectations, and a little bit sloppy about. So we have kj of b. Then we have minus. So we have an additional term to what we had before. We have this jbb term. And then there's again the delta I to the b term, which we already saw is given by which in expectation reduces to qj, or I guess q of b. So that's what we put. That's the q of b is what we're putting in. Oops, into the v coordinate. So there's this additional jbb term, but we're allowed to pick q of b however we want. And so we can just pick this q of b to cancel the jbb term and put the log in back. So, so this is also one minus log b k of b if you pick q of b to be basically, well, JBB, maybe there was, I think maybe there was a minus here. Well, then it would be minus JBB. So the signs are likely wrong here, but it doesn't matter. The point is that we can pick it in this way, cancel the JBB term, and so that the whole thing again reduces to a 1 minus log. So this is basically it in this finite range approach. To some, the upshot is this mechanism when you see this the first time, I understand this will look a little bit. This looks a little bit strange. I felt the same way when I saw this the first time. But I think it's an incredibly general principle at work here. Large sets contract anyway. We saw that. Blocks are not problematic because we can adjust the explicit part V of B as we need it. And small sets, in fact, are also okay because this representation, there's a flexibility. So in fact, you can also cancel the small sets. So expanding parts are canceled from all small sets. Okay. There's much more that could be said about this. I could give you the proof of this. It's not difficult. It's the same kind of combinatorics I've done before. It's a little bit more involved, but it's more or less the same. But I think it's probably best that I take a break soon, and after the break, I'll explain an example because to give you, I mean, to return a little bit to the kind of motivation for all of this. So there's many things I haven't explained. What I have explained is the general principle how to deal with how to localize the remainder in these approximations. I haven't explained what really the good choices of the norms are. The one I gave you for fermions is pretty close. The one for the L infinity norms for bosons was too much of a simplification, as we saw. I haven't explained so these order V plus K squared terms, I wrote them as V plus K squared terms in the sense that if you write down the formula, there's at least two factors of V or K. You need to do the combinatorics of where these factors are coming from and so on. That's a little bit tedious, but it's not, it's in principle elementary. I haven't explained how you get from this to correlation functions, etc. But what I've tried to explain is somehow the heart of what's happening. And I hope I can maybe illustrate this with an example in the last hour. And if you want to learn more about this, well, I've put references on the website, and I'll put more references later as well. And if you want to need to see more details, you have to ask me after these classes. So let's take a break now, and then I'll continue with something a little bit less technical.
Okay, very good. Maybe if there are questions on this first part of the lecture, it's a good time.
Can I just ask one question, please?
Yes.
So the first part you're going to remove, I mean the blocks you're going to remove in the measures are going to shift a bit your parameters?
Yes, so this Q basically is, so this formula Vj plus the first term is basically first order perturbation theory, right? We're just taking the expectation, and that gives what explained in lecture 2. And this Q, yes, it's a sort of it's a little shift of the parameters that comes from all of the non-local part at every scale. It's not, these coefficients are not going to be explicit, or they're going to be explicit in terms of these Ks, but we're never going to have explicit controls of these Ks. So these are somehow the non-perturbative corrections you need to make to naive perturbation theory to get a contractive estimate.
Okay, but so the blocks and the small set will contribute, or only the blocks?
Yes, the blocks and the small sets. So this formula for so I've told you, you pick Q of B to be minus JBB plus log B of K. But if you really write down what it is, it's um, um, it's something like, so JBB was minus the sum of, so JBB was given by this, right?
Mm-hmm.
So let's put that here. So the minus goes away. And in fact, so this JBX is in fact log x b k of x. And well, the second part, log, is just removing the constraint that we're not taking out the blocks here. So it's really this. It's the local part from K associated with a block, and for all small sets that contain that block.
Mm.
So we're interested in a block B, and what the non-perturbative or this non-local correction you need to make is all blocks, say like, or all small sets, say like this, that contain that block. So X is this, and B is that block. So you're summing over all of these sets, and those are the corrections you need to put into the local part.
Mm.
And here it matters that, I mean, there's this local decomposition of this part.
But you need to follow precisely only the blocks for the parameters.
Yes, well, these will give parameters that are only associated with the blocks, because this the part from a small set K of X, it can be decomposed into these parts, which are only, so it's only going to be sum over blocks here.
Mm-hmm. Mm-hmm. Okay. Okay.
But it comes from all, so you have a block, all the small sets around it will contribute to the evolution of what happens on the block at the next scale.
Yes. Yes. Okay. Yeah. Okay. Okay.
And yeah.
No, thank you. Thank you. Okay, it's clear.
Yeah, I mean, this is at least for me, this part is not easy to comprehend what's going on here the first time you see it. But I think this is really the crucial point. All of once you have this, there's usually a lot of technical work to make this method work, but sort of that you can make it work. The conceptual problems are these, that you can compensate by blocks what happens even outside for non-blocks.
Is it crucial to treat this large polymer separately? Why couldn't you just
yeah, that's a good I think that's a good point. I mean, one reason is because it's easy to, I mean, separate. Really, this argument here is much easier than correct cancellation. But I think you're right that one loses a little bit of precision by going in this way, treating them separately, using just that they contract. And at the level of precision we're interested in, we don't need to know more about these. But of course, if you were to treat them on a more equal footing, you could have a more precise I mean,
that was my second question, in fact. So suppose that I want to compute RG running of the quartic coupling. Which polymers contribute? Is it just the single block polymers or all polymers?
No, it's so if you want, so say the quartic coupling. So in this scheme, at every scale, they well, you have the block, and you have the small sets around it that feed into the next coupling. So it's not just a block, but it's sort of the small set neighborhood that feeds into it. Then you go to a bigger scale. Eventually, every polymer, as large as it is, eventually will be in a small set, right? Because it's at some scale, and then it gets reblocked, and in some sense, it's going to be in a huge block. So somehow all of the non-local contributions, they eventually enter these renormalized coupling constants, but they do that at a scale when they become relevant. They don't do this all at once. So this is maybe different to what you have. So in a more perturbative way, you'd like to have, say, the beta function to all orders having all phi-4 contributions in the phi-4 coupling, right? In this scheme, they will stay in this K, which we don't need to know much about, for as long as possible, and then there will be a scale where they become important. And then they will, at this point, they'll go in. But it's arranged in such a way that they go in at the point when their size is of the right order.
Well, this a bit disagrees with what I know from some examples. So for example, in some examples that I'm familiar with, if you start with a phi to the 4th interaction, you do a single RG step, you're going to generate some particular kind of phi to the 6th interaction, which is not going to be fully local, so you are going to have to put it into K in some form, I guess.
Yes.
And then when you do the next RG step, that phi to the 6th non-local, not fully local interaction is going to feed into the phi to the 4th.
Yes, that's correct.
So my question.
So that happens here too.
And you have to do it carefully in order to compute the correct running of the phi to the 4th coupling.
Yes.
So my question was, this not fully local phi to the 6th interaction, does it leave? Is it going to leave? I'm just doing two RG steps. So this, and I'm just wondering which polymers are going to enter the game. Is it going to be polymers of some limited size or arbitrary large size?
Well, at every scale, it's limited size. It's these small sets. So they have limited size at every scale. But so of course, there is also a phi to the 6 or phi to the 4 term in a huge polymer that, say, goes around the whole space, right? These polymers do appear. They'll have a tiny weight. They'll have like many factors of the coupling constant in it, if you want. Like the bigger the polymer is, the more factors of the coupling constant would be in there. So they're very high order. These are not corrected by the flow up the coupling constant at this scale, but will remain an error term until the scale where this huge polymer actually becomes a polymer of size 1. So one of the beauties of the principles I just explained is that they're really very general, and they apply to a lot of problems, including some of the ones I mentioned in lecture 1, phi-4 type models, Sine-Gordon or discrete Gaussian type problems, models, etc. And to make this more concrete, and also to end on a lighter note, and with the opportunity to explain a new conceptual point, I will end with an example that I studied with Nick Crawford and Tyler Helmuth, which is the zero-state Potts model. So what is this model? This is a percolation model. So as before, we're going to be on a torus. We're looking at the 3-dimensional case. The 2-dimensional case also something can be said, but it's different. So let me focus on the 3-dimensional case. So this is a percolation model of forests. So we have the torus, And we can consider subgraphs. That would be the usual Bernoulli percolation model. And the percolation model, we're looking at only subgraphs which don't have any cycles are allowed. So these are called forests. And the probability of such a forest is proportional to a parameter beta, which is a positive number, to the number of edges in that forest. So this model is what I will call the zero-state Potts model, or maybe more precisely, it's the Q to zero limit of the random cluster model, which is the representation of the Q-state Potts model. And so it's a percolation model of random forests. And the main question from the percolation point of view is, well, what the geometry of these forests are. How big are they? Is there a percolating one that is spanning over all distances? And so what can be proved is the following. When this parameter beta is small enough, it's in fact easy to see that all components are small. It is the case that these forests are dominated by ordinary Bernoulli percolation. They're all small if beta is small. That's easy to show. It's a high temperature argument. Where the renormalization group plays a role is the low temperature case when beta is large. So in this case, what in 3 dimensions or higher, what these methods can be used for is to show that say the percolation probability behaves like, well, the first term is a constant, theta of beta squared. And this constant theta of beta is 1 minus order 1 over beta. So it's positive if beta is large. And then most interestingly, the correction is it's free field like. And then there are lower order corrections, which are something like this. There is a lower order in x decay, and then there's also a finite volume error. In an ordinary Bernoulli percolation term, well, the first term would look the same. You have the connection probability behaves at low temperatures asymptotically like a constant. But in this model, as opposed to ordinary percolation, the corrections are polynomial. They are free field-like. And so it behaves in much like a Heisenberg model rather than an Ising model at low temperature. And the methods I explained in the last lecture and a half can be used to see this, but there is and let me briefly explain a point that appears here, which is a generic one and an interesting one, which is that of symmetry. So it turns out there's a beautiful observation that was made by Caracciolo, Jacobsen, Salur, Sportiello, and Sokol, which is that this percolation probability, so they didn't phrase it in exactly this way, but it's immediate from what they did. The percolation probability can be written exactly as a Grassmann integral. So, so this is as before, and then well, this X is not the same as this one. I hope this, well, maybe I should use different letter here. And there's an exponential of minus so this is an exact formula. It's not so hard to prove, but let me not do that right now. I want to understand this expression. So this looks like the model we've been considering. There's a free field term, like this one. In fact, it gets even better. There's a mass term. So in fact, it's a massive free field, and the mass is 1 over beta. But then there's also an interaction term, which is this one. It's a quartic interaction term, and one of the subtleties of it basically looks like a fermionic version of the phi-4 model. With the change that the phi-4 is not a phi-4, but it's two of the phi factors if I have an extra gradient in them. But there's an important subtlety, or it's maybe not a subtlety, but there's an important point. The coupling constant, 1 over beta, is the same that appears in 2 places. So if the coupling constant in front of the interaction term was much smaller than the coupling constant in the mass term, then it would be a standard application of a cluster expansion to show that correlations decay exponentially. But they turn out to be the same, exactly the same. And as we see from the result, there's no way a cluster expansion can work. In fact, correlations do not decay at all. They are constant to leading order, and only to second order they decay. But they don't decay exponentially, but they decay like a free field. So it doesn't look at all like a cluster expansion has any hope to work here, and it doesn't. And the reason is that the coupling that appears in these 2 places are the same. So it turns out that there are non-perturbative, meaning all orders, cancellations between these 2 terms that you could see to first or second order in perturbation theory, but they happen non-perturbatively to all orders. And it's not a coincidence. There's a hidden symmetry in this model. And so what I'm going to explain is that really to all orders, there's a cancellation between the red and the blue term, which has the effect that the mass completely, exactly, with no approximation, cancels, and what's left is this free field behavior, but only to second order because there's also a constant part. So there is a hidden symmetry. I'm going to explain what this hidden symmetry is. roughly speaking, what I will explain is that this model really looks not like an Ising model, but like a Heisenberg model where the spins are on the sphere, and the kind of symmetry you have is like the rotational symmetry that you'd have in a Heisenberg model where you can rotate spins. It's the same kind of symmetry that appears here. It's a very close analog of that. So there, so maybe at this point, I should, and so this is a generic feature that happens in models we're interested in, that they have symmetry. So the Heisenberg model would be one. This one, as I will explain, is another. All models we're interested in have some kind of symmetry, which plays an essential role in understanding them. And when you do the renormalization group, you have to be careful about the symmetry. If you're not careful about the symmetry, you're not going to go anywhere. And there's really two options to deal with symmetry.
So why are you saying it's a hidden symmetry? What's so hidden about it?
Okay, well, I'll explain it. I mean, at this point, you don't. It's not obvious that the symmetry is the supergroup OSP12. That's what I mean by hidden. Maybe it's obvious to you, but it wasn't obvious to me, and I'll explain it so that it'll become obvious. But there's an OSP12 symmetry here. That's what I call hidden. But does that make sense?
But it's exactly present at the level of this action. It's exact.
Yeah, there's an exact OSP12 symmetry.
Okay. Okay, thanks.
So there are two options to deal with symmetry in RG. One is to, so the first point is you always have to be careful about symmetry. The first way, which if you can, is perhaps the better or the nice way, is to preserve the symmetry along the RG flow. So this principle works, and so for example, if you have a phi-4 model that has a Z2 symmetry, critical phi-4 model with a Z2 symmetry, in this case, it's easy to just preserve the Z2 symmetry along the flow. But there are other examples where it's not so easy to preserve the symmetry manifestly along the RG flow. So examples are, for example, non-abelian gauge theories. And this one is also one where we wouldn't, or at least I wouldn't know, how to preserve the symmetry along the RG flow. And well, there's a second way one can handle this, which is, well, not to preserve the symmetry along the flow, but to enforce non-perturbative cancellations, which are due to the symmetry using Ward identities. And so, for example, this is an idea that has been used very successfully by the Italian school, Mastro Pietro, Giuliani, Galavotti, Benfatto, etc., in the study of 1 + 1 dimensional Fermi systems. So let me explain what it means in this context. So the above Forest model, so Forest model is the same as zero-state Potts model, is in fact the same as an OSP12 nonlinear sigma model. And this, to the physicists, this will not sound intimidating. To the mathematicians, this term may sound intimidating, but in fact, as I'll convince you now, it's very elementary. We start with 2 Grassmann variables, per vertex. I'm going to denote them by psi and eta. They're essentially the same as the psi bar and the psi. I'm just going to use different letters now because the psi and the psi bar are going to be rescaled versions of these. So these are Grassmann variables. Well, then you can define another, in terms of these, you can define what I'm going to write as zx as square root 1 minus 2 psi x eta x, which is by definition of just defined by expanding the square root. So it's 1 minus psi x eta x. So this is an even element. So of the Grassmann algebra. So it's commuting. The psi and eta, they're anti-commuting. This one is commuting. And we can formally unite them into a supervector ux, which has components formally psi x, eta x, and zx. Now, the observation is that ux dot ux is equal to -1 if I define ux dot uy to be eta x psi y plus eta y psi x minus zx zy. And this is what is called the OSP12 inner product. So you should really think of it as an analog of the Euclidean inner product. It's some kind of a natural analog in the sense that for fermions, the analog of a Euclidean inner product is what I wrote here, which is the symplectic one. And so that would be SP2, and it's called OSP12 because they're also the even variables z here. Anyway, if you don't like the fancy terminology, this is really all there is to it. This is the definition. They satisfy this constraint, ux dot ux is equal to 1 with this definition, and we think of this as an inner product. And OSP12 is just by definition all the transformations of the Grassmann algebra that preserve this inner product. Just like the rotation group is all the transformations that preserve the Euclidean inner product. And there's a version of the Grassmann integral which is invariant under these symmetries. And it's simply the usual Grassmann integral. With an additional factor 1 over zx. And I write this as the integral over h02. Never mind this terminology, but this is somehow the analog of the Haar measure on the sphere. The rises in exactly the analogous way. And then, like the Heisenberg model, we can define a model of these spins, which we think of spins. We could put an external field as well, and it's given by this invariant integral, and then we put exactly the same action we would put in a Heisenberg model. With a magnetic field, say. And so here all inner products with respect to the dot from above. So that really means sum over edges xy ux minus uy inner product ux dot uy minus ui. And it turns out that the above proposition, the one due to Caracciolo, Jacobson, Salur, Sportiello, and Sokol, can be reformulated as follows. The probability that 0 is connected to X, is equal to minus the inner product of the spin at U with the spin at X, with the external field 0. And you obtain the formula I wrote down here by simply setting psi bar is equal to square root beta psi X and psi as square root beta eta X. But in this representation, this OSP symmetry, 1, 2 symmetry is manifest. It looks like a Heisenberg model. You should think of these UX, they're fermionic, or they're sort of super vectors, but really you should think of them as maybe being on the sphere. And correspondingly, you have relations between the components. At the level of correlation functions, they result in word identities. So what do they mean? So they mean, for example, that the inner product of U0 with UX is the same as, well, the transversal one. So say Z0 ZX is the same as the, well, this is the longitudinal one, is the same as the transversal one, like this. So really what this means is that if you have a rotationally symmetric model, it doesn't matter if you, in which tangent direction, say you take you look at the correlation functions, or if you look at the radial ones, they're all related to each other. That's exactly what these relations say. They're just an analog for this model of what is happening in the Heisenberg model, and they're derived in exactly the same way. Just putting these fermions rather than. So you have these relations, and another one is the sum of the 2-point function. Now with an external field H is related to the magnetization with a magnet this way. So you have these word identities. They result from the OSP 1-2 symmetry. So that's what I mean by hidden. From this formula here, all these, so these are a number of non-trivial identities between the correlation functions, which are not obvious from, at least not to me, from this formula up there. But they have a geometric interpretation, and they come from a hidden symmetry, or they come from a symmetry. And so in RG perspective, they're essential to take into account correctly.
Excuse me.
I'm not. Yes.
Is it to see that the two models that you describe are the same?
You mean this one?
Yes.
No,
the original one. So the
forest
model?
one and this one.
Yes.
It's not. No, it's not obvious. Once you know it's true, it's not very hard to check. But a priori, at least to me, it's highly non-obvious that they're the same. This is really Caracciolo, Jacobson, Solera, Sportiello, and Sokol who observed this. I can explain this later if you're interested. It's not obvious at this point at all, but it's true. And once you know it, it's not very hard to check. Yeah.
Okay, thanks.
So I'm using this. Right. So in fact, these identities, some of them, they have combinatorial That's a good remark, in fact, that you made. They have combinatorial interpretation at the level of the percolation model. And these identities, you can check them at the level of the percolation model by doing relatively simple combinatorics. But they have this geometric interpretation here. So so what do we do with them? So, well, the upshot is, well, the message I want to make is that you need to take these things into account when understanding the renormalization group. If we go to this representation here, we go to the point of view I explained. We look at some kind of a Gaussian part, and then we look at some kind of perturbation, and we decompose the Gaussian part. Well, when you do that, you break this OSP1-2 symmetry. The renormalized model doesn't have this symmetry. So that's what I mean by so if we proceed in this way, we do not preserve the symmetry along the flow. One has to, and so instead what we do is we have to use these constraints imposed by these identities to restore the symmetry in the end. So roughly speaking, if we go back to the psi and psi bar variables, so they for example, Z naught is just the expectation of 1 minus psi 0 eta 0. That was by definition. So this is 1 minus 1 over beta psi 0, psi bar 0 psi 0. Psi x eta y similarly is just 1 over beta psi bar x psi y. So these relations provide constraints on the correlation functions. And in fact, if you inspect them closely, you'll see that they're somewhat concerning constraints, because we're assuming, well, the hope is that there's a Gaussian part, and where we'd like to treat the model as some kind of perturbation of a Gaussian model. But these constraints, they'll tell you something like that the 2-point function is equal to a 4-point function, and things like that you cannot have in a Gaussian model. So that looks a little bit concerning at first. And it turns out it's not a problem. So the general form of the model above is a relatively simple model of these fermionic variables. It has it has the following general form. There's the Gaussian part, which I wrote like this. Maybe I should write it like that. So it's like a free field part, and then there's some interaction part, which generically has coupling constants we put, and I'm putting generic ones. So generically, it looks like this for suitable choice of these parameters, M, Z naught, A naught, B naught. But in fact, for very specific choice of these. And the way we can go about studying the above model is by first studying this general model with general parameters and see what we can say about it. And so here's roughly what one can the kind of theorem that you can prove using what I explained in the kind of ideas I explained the last 2 lectures. So this is the kind of theorem you can prove. Given B naught bigger than 0 small, M positive, there exist various parameters. One of them I call Z naught C. It depends on B naught and M squared. It's of order B naught. There is another one, A naught C, B naught M squared. So these are coming out of a stable manifold condition. And then to state the full result, there are also various other parameters that, or various other constants that appear. So, for example, there would be one that be called lambda, which is 1 minus order B naught, I think. So you can get various estimates on these. So another one we call A n tilde. Another one U n tilde, etc. So anyway, the point is we can you construct all these functions. So this is what do they satisfy? Well, we can then express the correlation functions in terms of these finitely many functions we construct. So for example, the 2-point function, say the 2-point function on the diagonal, is given by, well, what is it given by? Well, it's if the z naught and the a naught are chosen to be these critical values, well, then the 2-point function on the diagonal is given by what? Well, it's given by a free field 2-point function on the diagonal with the same mass m, so that's good. That's the first term. Note there's a subtle, there's a, I'm writing ZD here. So a priori, we're always looking at a finite torus. And there is an important difference if you look at the Green's function on a finite torus or on ZD if you want to take m to 0. One blows up, the other one remains bounded. This is the one that remains bounded. So we're not approximating by the free field. So the first term is not the free field 2-point function we're putting in, but it's the infinite volume one. And then there is a second correction term, which roughly speaking looks like this. There's a volume factor in this, and you get something like this, and then further error terms. Now, what happens is that if you first take the infinite volume limit, and then m to 0, then the second term, this one, will go to 0. So it goes to 0 if n goes to infinity with m bigger than 0 fixed. So in other words, if you first take the infinite volume limit and then m to 0, the second term doesn't play a role. And you just see the infinite volume free field 2-point function. However, what we want is we want to take basically this h parameter in the model to 0 in finite volume and then take the infinite volume limit. And it turns out what happens in this case, the main contribution comes out of the second term. Well, then there's various other correlation functions. So these relations are ones that are given in terms of these parameters we construct. A priori, we don't have sufficiently good control of what all of them are. And so you get a similar relation on, I'm going to finish in 2 minutes. I said I wouldn't go over, so I won't. You get similar relations for these quantities, and the conceptual message is well, we can construct all of these quantities in terms of finitely many parameters, and then we can apply all these word identities up here, and they basically. So the number of parameters we construct, there may be 5 of them, and these word identities basically make them all collapse to about 1 or 2. And what happens is that the symmetry which we've broken by running the renormalization group gets restored. And for example, we can see things like the leading one term here, which is sort of an effect that is really comes out. I mean, where the symmetry plays really an important role, so that we can see it. I know this was a little bit quick, but I wanted to end at a point where I haven't given you the details of how this works, but I wanted to end at a point where there's, I think, a conceptually nice thing happening, how these symmetries interact with the renormalization group. Let me finish here, and if anyone is interested in learning more about any of these things, do get in touch with me. We can meet separately.
Thank you very much, Roland, for all these lectures. And are there questions on this last part, or on any other part of the lectures?
Can I ask a question about this? This thing that you are saying that you cannot preserve symmetry for this particular model when you do RG.
Yes.
So this is related to the fact that the symmetry is, as we say in physics, realized non-linearly. That you have this non-linear sigma model.
Yes.
So if you had a linear sigma model with OSP once,
yes. So
would that be a problem?
So I mean, what we do, we wouldn't know how to do that, but say so for this OSP 1-2 model, we don't. I mean, you could somehow realize the symmetry linearly by embedding this space into a higher dimensional space, but we would not know how to analyze this. It looks very hard from my perspective anyway. You get a bosonic field, etc. It looks very difficult. It looks at least as difficult as, say, the case of the Heisenberg model. So the one I mentioned in lecture 1. So formally, the model looks identical to the Heisenberg model. What Balaban does is he does realize the symmetry linearly by embedding it in a higher dimensional space, and is able to preserve the symmetry along the way. But this uses that basically it's a compact symmetry, and OSP 1-2 is non-compact, and I wouldn't know how to do this with a non-compact symmetry. And
so you're saying for you it's easier to suffer a bit with not fully preserved symmetry and plus word identities rather than.
Yes, and my impression is that this is happening in various cases, that it seems, well, a priori, and in some cases it's clear or easy to see how to preserve the symmetry along the renormalization group, but at least I don't know how to do it in most cases, or in many cases it's not clear to me how one would do that. And well, and so for example, these so in particular, for example, these non-compact symmetries, I wouldn't know. I mean, I think also non-abelian gauge symmetries. I think the methods that exist there, they do not succeed in preserving the symmetry along the flow, as far as I understand. So one way is not to do it and reinforce restore the symmetry effectively through word identities. But yeah.
Thank you.
I have a very, very naive question, because the last part was really too fast for me. So
yes, I'm sorry.
Could you please say what the K that you construct in the, say, in the abstract part would look like in this case for the percolation model?
Yes. So So basically, let me see. So we start from the field theory of this type. So we have a Gaussian part. That's the green part here. So that's like a free field part, Laplacian plus m squared of the type we had before. We can decompose it. This is going to be our initial V naught.
Yes.
Our Vj, so this is going to be V naught of lambda. The Vj at every scale will have the same form as this. So it will be of the same form as this, but the coupling constants will be adjusted. And the K is what comes out of this abstract procedure that from the last lecture or the last hour, basically. There's no, I mean, it comes out of from this general formula that I wrote down. We don't have any explicit.
So they are not explicit.
They're not explicit at all. What we have is estimates on them.
Okay, and in which functional space will you estimate?
Yeah, so they are in a functional space that's roughly. It's not too far. It's a bit more involved than. So the norm I wrote, this one, that's pretty much the norm. There's some. This one, right? Every function of these fermions can be represented in this way. So if you have a function of the fermions in the set X, so it's just a polynomial, formal polynomial in these psi X bars with some coefficients F, which are antisymmetric. We can define this norm that I. So this norm.
Yeah, the analytic norm. Okay.
So this norm, so basically this analytic norm. So that's really the advantage of the fermions, that one can use this analytic norm basically, and it has all the properties we need. It has this. So I showed this integration property here. It has the and you can imagine, because it's an analytic norm, it's not so bad to get these type of properties. They're kind of Taylor expansions.
And these, for the part regarding the localization, it's
yes. So because it's an analytic norm, so basically this localization is a kind of a Taylor expansion, and 1 minus loc is a kind of a Taylor remainder. And because the norm is analytic, you can you can get a very good estimate on this Taylor remainder. So these factors L to the minus D. So maybe that's a part I haven't explained. Why do we get a factor L to the minus D here in the Taylor remainder? So that comes from the fact that in these norms, sorry, I'm moving back and forth, but so these norms, they have a parameter H in here. So this parameter H will be chosen, roughly speaking, it's L to the minus D minus 2 over 2J. So somehow the analyticity radius is that we need is getting smaller and smaller, because the fields that are getting integrated are getting smaller and smaller. That's where the assumption 3 dimensions helps, for example, and so when you're roughly speaking, when you do the Taylor approximation and you subtract the 4th order part, well, you'll have a bunch of these L to the minus J factors left, and they you subtract enough so that you get an L to the minus D, and that's roughly why you keep a 4th order term and nothing higher, because that's enough to get an L to the minus D error. That's roughly what how it works, so then we run basically this procedure I explained in lectures 3 and 4, and the K will get smaller and smaller. The V part will evolve according to first order perturbation theory, with these errors feeding in from the K part at every scale, and one has to work a bit harder to get, so that constructs the renormalized potential. One has to work a bit harder to get to these correlation functions, but you can, and that, yeah. So that's not quite immediate, and I didn't explain at all how that works, but it can be done. Does
and
that
then I have a very unprecise question, say on the method.
Yes.
When do you expect this method to work? So I guess that you cannot use this renormalization group for all models, right? And so what are the features of the typical model for which you can use this method?
Yeah, I mean, so the way I presented it, it starts out, it has to be written as a kind of a field theory, right? So for example, so that's the starting point, and that's a restriction. It turns out it's less of a restriction than you may think it is. So for example, this applies to, for example, a two-dimensional Coulomb gas, which doesn't look like a field theory initially, but which you can actually write like one. And so one can use that to study models like that. But that's the starting point. And then once it's written as a field theory, in principle, and that's one of the beauties of the method. In principle, the formal part more or less always works. The question is, can you control the errors? And that depends from model to model. Somehow these mechanisms, the choice of the norms, the mechanism for the contraction, and so on, there's a good guess, or from basically the physics literature tells us what we should expect, but whether one can control it or not is delicate from model to model.
So, for instance, if you have an interaction which is not not polynomial, but I don't know, something which is very nonlinear, then you can hope to do the same, or it's just
yeah, in principle, yeah. So, for example, models that have been studied are what are so basically like a free field, but you put a general function v, which is a function of the gradient of the field. For example, this is called the gradient model in the literature, and v is if v satisfies certain estimates, you can run the same thing, and the estimates is v needs to be a function of maybe a C10 regularity with a certain bounds on the derivatives or something like that. Then these kind of things go through. So it, in that sense, so these polynomial examples are sort of the prototypical models for much, but basically once the k is generated, it is so complicated. I mean, the formula would be so complicated. You don't. I mean, we don't want to use that it's a polynomial. It's not going to be a polynomial actually, because it's going to live in some function space. And so you can start with anything that's in a sufficiently good space, basically. But these polynomial models are kind of the prototypical models that the simplest to write down.
and you don't need any scaling condition or something like this in order to have this result that at all levels you expect, say, the v to have always the same form. So means somehow that you have a kind of effective coefficients. And
yes, you definitely. Oh, sorry for interrupting.
I just would expect that in some situation, in some physical system, this should not be the case.
Well, yes. I mean, there's of course problems where this is. I mean, you can do the first step, but then you realize that basically you cannot control the first, the explicit part. So, for example, if you did a three-dimensional Ising model, the fixed point that we expect there is not that. So basically, the kind of models I explained is models which are sort of driven in some sense to a Gaussian fixed point. Say the three-dimensional Ising model, what is expected is the fixed point is non-Gaussian. It's very complicated. You can do the perturbative calculation, but it's not going to be valid. I mean, you're not going to be able to get close. I mean, somehow this perturbative calculation is useful if you can always stay close to the fixed point, say in the conceptual picture. But it's ultimately a perturbative calculation around the Gaussian model. Well, if the Ising fixed point is far away, the method, or what I explained, is not going to be sufficient to understand how to get there. There are some toy cases, I guess, where.
But
so I mean, there's.
That it's not going to be sufficient. Why? Suppose that you are very ambitious and you are willing to look very carefully at what happens with this K, and maybe work very hard to expand things to high order and do many more explicit calculations than what you did. Maybe.
Yeah, I mean.
By analyzing many first terms explicitly, many more than you did here, where you just keep track of three coefficients. Is it clear?
Well, I'm not sure if it's clear or not, but I mean, definitely it would involve ideas that go very significantly beyond what I explained. I mean, so for example, what is doable and has been done is something like this Wilson-Fisher fixed point in 4 minus epsilon for epsilon very small, right? So if we go back to, well, I guess the picture doesn't help much, but ultimately all what I explained is based on perturbations around the Gaussian, right? And at least I mean this. I don't know how one would use it in 3 dimensions, but I agree. It's the right. It's the
problem for the future.
Yeah, well, it's a good homework. Yeah. I mean, there are these cases where, in hierarchical models, where these things have been studied, right? So for hierarchical models, I guess there are various works that have looked at non-Gaussian fixed points which are far away from a Gaussian by using numerically assisted computations to get into the vicinity of the fixed point, right? I forgot like who.
Those works are 50 years old, and it's time to go beyond.
Yeah, I remember there was a recent one by Galavotti and Jauslin. Maybe they looked at the Kondo problem recently, hierarchically. Something like that. I forgot. I was only in a talk a few years ago about this, so I can't really say what exactly they did. But indeed, all of these things are not. It's not. And it relies very much that in the hierarchical case, you're looking at the dynamics of a single variable function rather than basically this infinite dimensional one, right? So I don't know.
Well, I suppose it's possible that if you allow something more more complicated than polynomials, but still local, like you could choose the e to the minus v approximation to involve some unknown functions of the field phi at a point, a sum of an unknown function f of phi at a point, and then the gradients as usual. You might be able to choose those f's. We do have, I mean, the general formalism does allow you to find out what the modification to the f would be from the small sets and the single and the blocks. But you'd have to have a good guess as to what that function f should be in order to have any chance of showing that the k is contracted still. And one thing you should maybe I should point out is that the k is an independent variable in the dynamical system. That's why we don't have a formula for the k. It just evolves according to the dynamical system, which involves involves the coupling constants, or in some more general formalism, just the form of the local function f, which I was talking about a moment ago. And then there's this k as well. And that dynamical system has to be understood.
Yeah, it's very interesting, David, what you're saying. It would be great if, what you're saying is that, okay, there are some people doing these numerical calculations using local potential approximation. And in some cases, they seem to work pretty well. So perhaps it's a sign that some rigorous work could be done in that direction.
Yes, for the next generation after me.
Well, I mean, a much more modest and question along the same lines is that for hierarchical models, we understand pretty much all models can be studied hierarchically pretty well. I mean, all the ones I explained on the first slide, I mean, they're all doable and they're not too bad, including the nonlinear sigma model and so on. And unfortunately, when going from the hierarchical model to the non-hierarchical model, the complexity seems to increase by a tower function or something like that. And it would be a much more modest goal than going from the hierarchical 3D easing model to the real 3D easing model would be just in these simpler cases to make better use of, say, the simple understanding the hierarchical models or something of that sort, I think. I mean, in some sense, this procedure, this finite range approach is pretty close to the hierarchical model in the sense that the one is really the hierarchical model strictly becomes a simplification of this model. You basically get rid of all sets which are not blocks. All small sets go away, all large sets go away. You're just keeping the blocks. That sort of defines the hierarchical model in this procedure. And an appealing conceptual point of this setup is really that the hierarchical model arises as a strict simplification, literally. And when you study the hierarchical model in this language, really you just have to add more details to get the real model. But
is it just a simplification, or can you say that the real model is a small perturbation of the hierarchical model?
Yeah, so that's what I'm asking. It is a simplification. The whole setup is just strictly more general, but we cannot, or we have not succeeded in saying really that the real model is a small perturbation of the hierarchical model, or is a perturbation in some sense of the hierarchical model. That's the question I'm asking. Rather than saying that they're written in the same way, is it possible to really view the non-hierarchical model as a perturbation of the hierarchical model in some sense? And I mean, of course, it can't be so simple, right? I mean, many exponents are the same, but not, I mean, you don't have a field strength renormalization, the hierarchical model, for example. And that, in fact, causes a lot of the technical, I mean, that's a serious technical difficulty for bosonic models to have the additional field strength renormalization, but etc. So I'm not sure to what generality you can expect it, but
so here you have a discrete dynamical system. Would it be more difficult to have a continuous dynamical model?
That's also a very nice question, and one that I'd love to understand better. So the issue is I mean, well, conceptually, and also the perturbation theory part, as I explained in the first lecture, is all of this seems somehow nicer in the continuous parameter setting. But these kinds of technical ingredients here, this reblocking, the contraction of going from one block to the next, is well, I think it's fair to say, correct me if I'm wrong, David, but no one has succeeded in doing all of this directly continuously.
No, in fact, I made a horrible mistake by trying to do that. I tried to do it even for fermions, and I made a mistake that's more or less equivalent to thinking that the square root of an increment is the same size as the increment, which of course is overlooking the basis of Ito calculus. Anyway, it was a it's not so easy to directly use the differential equation as it is to use the integral form of the differential equation. And that's even true for theory of ordinary differential equations. I think all of the existence proofs proceed by converting them into integral equations and then doing some kind of fixed point theorem. They never directly use the differential equation to estimate itself, do they? But there is something you could do continuously, which I think would be challenging, but it's so interesting. So Roland derived the finite range decomposition by taking the covariance and decomposing it into an integral over finite range covariances. And then he grouped the integral, which over the variable t, I think he called it, into ranges, which were scalings of each other, to get the actual decomposition that he used to define the zetas, the fluctuation fields. Now, what you could do is instead to write locally that the field phi is the integral of the increments of the field. Each increment would have the covariance that was underneath his integral decomposition with a dt times it. So it's a kind of Ito integral thing. But then what you would have to do if you want to use that, there'd always be a discrete, sorry, my voice is getting a frog in it. There would always be a discrete thing you'd have to do, which corresponds to the reblocking operation here. But I still think it would be interesting to take that tack if you can, because what you could do is use stopping times, just like we do in the theory of stochastic equations. You let the field evolve until the norm of the field gets too large, and you have a stopping time that detects that. And what would happen is that the integration out would proceed to different times. If you think of the stochastic time, the t is the indexing this Ito calculus. It would proceed to different stochastic times in different parts of the lattice, if we were doing this on a lattice model, and where it gets stopped by the stopping time. And then what you would do is to regard the places where it got stopped as being part of the K, because what's happened there is that the field has become larger than is probable. And so morally speaking, they should be a very small error. And you could try to get closer to continuous time. You'd still have to reblock every now and then. I don't know any substitute, easy substitute, like no one yet has succeeded in defining some kind of translation invariant decomposition that allows you to think of time. I mean, in other words, we use an L-adic decomposition of the the infinite volume lambda, and I don't know what the continuous time analog of that could possibly be.
I mean, maybe one point one other thing I could mention. So, for example, with Thierry and Benoit and so on, we have made use of the fact that the continuously evolving renormalized potential has, in some ways, is nicer than the discretely evolving one. For example, we used it to get, for example, Log-Sobolev inequalities for these kind of measures, and it was really seems to be essential to do this in continuous scale. But then at some point we usually have to resort to methods like this. It's not exactly what we used, but to actually control the renormalized potential at continuous times. We know its existence somehow a priori. It's always well defined. But then to get estimates on it, we basically run something like this to study it. We don't know how to. I mean, okay, I think I'm not very coherent here. But so, for example, for a 5-4 type model, one can get information on it, but not, to my knowledge, by studying it directly. One has to go through something like this, and then one can go back. But there's definitely something to be understood here.
Roland, can I ask about your forest model question?
Yes.
So if you applied those super transformations to the local to the you have this sum over you have the Gaussian part, the action looks like a Gaussian plus those 5/4 terms. Now, if you apply the super transformations to that, I take it that you generate extra terms by the super transformation, or is it invariant?
Sorry, can you say that again? Is it invariant if
under super transformations, is that form invariant, or does the 5/4 generate higher order things somehow? I don't see how it can, but does it?
You mean this one is invariant? The way this one I wrote down is exactly invariant,
right?
Yes.
Yeah. So the reason why I'm asking this question is because I take it it's only invariant because these are fermions. If you had bosons, then the fourth order term would generate new things under.
Yeah, so roughly speaking, the way you can see this, if you're looking at a Heisenberg model and you write it, say, in the stereographic projection, you expand. These are the first two orders you see, and then the higher orders from the nonlinearity of the square root. You see all orders. But in this, because of the fermions, it looks like a Heisenberg model, except that this gets truncated at a finite order.
Okay, then. So that gives me some insight into why this method, which relies on fixing the relationship between the coupling constants after you've run the renormalization group, is working. For the Bose case, if you wanted to try that, you would have to regard this action as in some sense standing for the whole nonlinear action that you would have to have in order to let the super transformations keep it. But maybe that's the role of the Ward identities, right?
Yes, you'd have again maybe the relevant and marginal terms in the Heisenberg model would be these two, but then you'd have a couple of more, I think.
Yes.
But so I think that wouldn't be a problem. The more serious problem is controlling the K in that case.
But maybe there's a way of imposing I guess we've talked about this before, and for some reason you think it doesn't work. You can't do the super transform. You can't fix the renormalization group so that each time you do a step, you can restore or you can impose ward identities on the next.
Well, I'd love to, but I don't. So maybe Slava is, if he's still there, he's someone who could help us there. Who knows how what can be done in that respect? I don't know how to say if you break. So if you write the model in this representation, you do the decomposition, you break the symmetries. How you can? It just seems to me you break it if you do this kind of thing. How do you find a better renormalization group transformation that doesn't break the symmetries?
Yeah, so what you want to do is to do a transformation that takes part of the K and puts it back into the V.
Well, I mean, first of all, if once you decompose the Gaussian, you break the symmetry, I think you just do. So, I mean, so if you do, say, a block spin transformation in extrinsic space, you can do transformations that don't break the symmetry, but we don't always know how to do that. And maybe Slava or someone else who's still there has a pointer on.
The intuition we use is that in physics we usually say these words that your symmetry is still there, but it's no longer manifest. So
yeah.
So the only control that you have over it is in terms of these identities that are still there.
So you also think about it in terms of the word identities then?
Well, I mean, yeah, we usually try not to do these things. I mean, usually we try to preserve the symmetry, and perturbation theory usually can preserve the symmetry.
But, right, but then you have to use like dimensional regularization and things like that, right? Is that
usually we get away with this? Usually, but I understand your pain, and I think I understand also your fix that you say, well, I can't see the symmetry, but it's still there, and it's encoded in this word identity, so I will not look at the action. Whenever I have to use the symmetry, I will just use the word identity, which is still going to be there.
Yes.
And I think there's nothing wrong with this philosophically. If you can get away with this, there's nothing wrong with this.
Yeah. Okay. Well, that's encouraging. I mean, for me, this point of symmetry is a very interesting one. I'd love to understand it better. I mean, partly because, so for example, this Heisenberg model is one that's still very. I mean, not this one, not the fermionic one I presented, but the Heisenberg model on the sphere, the bosonic one, is one that's very difficult to. Or the existing method that exists, which is Balaban's, is extremely complicated. And maybe that's unavoidable, but a nice aspect about to think about it is the symmetry aspect, which is not super technical, and maybe there's something to be learned how to do better. So in that sense, it's.
Can you remind me the dimension of this Heisenberg model you were talking about? It's a 2D Heisenberg model?
It's 3D.
Sorry, this is just a three-dimensional. So of course, the two-dimensional Heisenberg model, of course, that's a whole different story. This is just 3 dimensions. So the infrared problem in 3 dimensions, I mean, the ultraviolet problem in 2 dimensions should also be okay. But of course, the long distance problem in 2 dimensions, we don't know, or no one knows, I guess. The mass generation problem.
It's still complicated, even to show that in 3D, Heisenberg model flows to constant rate. But previously, it's still considered to be a complicated thing.
So this is in fact one of the models that got, I think, Caracciolo, Jacobson, Sokol, Sportiello, and Soler excited about this model which is, I mean, it's also supposed to have a mass generation in 2 dimensions. So exponential decay at all values of beta, which is a notorious mathematical problem in general, or a physical problem, I guess, as well, to understand. Well, in this model, it has a very it has this percolation interpretation, and there's in fact different ways to understand it in this model. So you can do the 2-dimensional RG computation. You see the beta function is positive or negative or whatever it has to be to predict the generation of a mass. But if you extrapolate the exact solution of the Potts model critical value at square root q to q to 0, you can also read off that the critical point should be at beta is equal to infinity. Anyway, I love, I'm just mentioning it because I'd love to understand more about this, and there's people in the audience who know a lot about this or related things. It would be a beautiful problem to understand anything about the about this question, and to this is good. This decay problem in 2 dimensions.